Well, good morning, everybody. How are we all doing today on this beautiful, beautiful day? Yes, morning, and it's a wonderful day, someone says in the chat. Fantastic. While I'm chatting with you, I thought I would throw up a question that people can start answering and start thinking about. In the meantime, yes, indeed, it is a beautiful day. I hope that everybody had a lovely, lovely midterm break. For me, it wasn't so much of a break as one might hope, but on the other hand, you can probably sympathize with that a little bit, thinking about midterm exams and stuff. That said, so I guess one of the things to announce, aside from the fact that it is actually, you know what, such a beautiful day. For those who are not on campus or are not in St. John's, let me just adjust my exposure settings just a little bit. Look at that. Beautiful. How often do you see that in St. John's, Newfoundland? Obviously, all the time in CBS, but St. John's, I mean, come on, not that often. Okay, so I did last night send out an email about midterm one. Midterm one has now been graded, so you should be able to see your grades there. Don't go and run off and check it right now. You can focus on the lecture right now, but afterwards, do check your grade. When you go in to look at your result, in midterm one, you should see a bunch of questions and what you got on each question. And if you haven't noticed this in the Gradescope interface so far, for each of those questions, you can actually click on the question and say, okay, why did I only get 7 out of 8 on that? And it'll show you in more detail, here is how you did on this specific part of this sub question, that you had, for example, well, that was a sensible type, but the justification for why that's a good type to store that piece of information is not so great, or something like that. For the final question, where I asked you to provide some Python code that would gather information about weather, you'll see that there are a bunch of different things that you could have gotten points for, such as asking the user how much snow fell, asking the user what time the storm starts, what time the storm stops, converting things to the appropriate type so that we're not trying to subtract strings, doing the subtraction to say end minus start. And you'll notice some other things. If your code calculated everything perfectly but didn't take into account the fact that you could have the storm could start one day and end on the next day. If you didn't take that into account, you got like 11 out of 12, which is pretty good. If you took into account the fact that the storm could have started and then gone on past midnight, then you get 12 out of 12. If you took into account the fact that the storm could actually last multiple days, then there's a couple of people in the class who got a 13 out of 12. So really well done there. There were a few people who had really excellent marks on the midterm. I think the highest was a 99.5. So nobody got that elusive 100 in this particular instance. The median grade was something like 79, I think, which is quite good. No, sorry, that might be for the course overall. Anyway, whatever it was, the median grade and the mean grades were both pretty, well, they were good. They were slightly higher than I expected. People often do well on the first midterm. However, we went a little bit further and did some more challenging material, like some loops and stuff, which we often don't get to in time for midterm one. And yet the median and mean grades were still quite good. So well done. I was actually quite pleased as I was looking through all of these midterms and saying, yeah, it looks like a bunch of people really got this. So good job, everybody. If you found that you really struggled and that your grade was not so great coming out of it, then two things. One, take a look through and see if there's any places where you say, oh yeah, I could have gotten that right. I just misunderstood something, or I didn't answer the question very well. Figure that out. Or alternatively, figure out, are there places where you really kind of struggled with the material and you need some help to catch up on it and to understand it. And if that is the case, then please don't hesitate to reach out. Myself, the lab instructor, the TAs, the tutors in the Success Center, the SI leader, there are so many resources for you. There are so many people who are here to help you do well in this course. So please reach out if you're struggling. All right, so that is it for the midterm. Overall, really good job. So let's see, we've got answers are coming in to my Top Hat question. In the meantime, we also have some chat, and the chat is, yes, more happy 28th of February. It's the 28th of February special for people. It's my sister-in-law's birthday, so happy birthday to her, but I don't know, is it a special day for anybody else here? Some of the reactions in the chat, I'm thinking maybe it is. Oh well. Okay, so I'm going to go ahead and close this question now, and if you didn't have a chance to finish it, that's okay, because we will have a chance to do this as homework later. So, what will the following Python expression evaluate to? So, what is this Python expression? Well, first of all, this is a list comprehension, so we're constructing a list of values. So, we are going to look at all of the values in the range from 0 up to, but not including, 100. And we're going to, in that range, we're going to choose all the values for which I modulo 10 is equal to 0, which means we're going to choose all of the values that are divisible by 10. So that's going to be 0, 10, 20, 30, 40, 50, 60, etc. up to 90, not 100, because remember, range is exclusive of where we count up to. And then we're going to compute what is I modulo 5 for each of those values. So what is, let me pull this up. So what is 0 modulo 5? Well, 0 modulo anything is going to be 0. How about 10 modulo 5? How about 20 modulo 5? Well, it looks like we are going to mostly be correct. That the answer here is this is a whole bunch of values. So this is going to give us a list which is from 0, 10, 20, 30, 40, 50, 60, 70, 80, 90. Okay, so that's a list, and we can add it up with the sum function. And the answer is going to be 0. So good job, most folks had that. Well done. Oh, one other thing I should say, over the break, again, sorry, let me put myself back up there. Over the break, and again I say break, between things like marking midterms and making up midterms and also doing a bunch of other stuff that had been kind of ignored for the past few weeks but really needed to be done. I'm a little behind on my email for this course, and I noted that a few people had issues with assignment 2 and Thonny specifically, because it turns out that in Thonny, when you paste Unicode characters like a green box or a yellow box into Thonny, it seems to crash. So sorry to find that that is the case, and that was a bit of an issue for some people. So one thing is I'd recommend maybe checking out a different IDE, at least for this assignment. And, Thonny is really good to start with, but there are things that are a bit more advanced. So, for example, Visual Studio Code is something we use in the lab, or there are other things on the course website. And I would suggest maybe checking out one of those other IDEs, because apparently Thonny has some limitations when it comes to things like Unicode support, which is slightly surprising to me, but it is apparently true. So, someone says Thonny was pain. Okay, we've got a recommendation here for Spyder in the chat. Great. So Spyder or VS Code or well, I don't know. There are a bunch of options on the course website under the resources page. So do check those out. All right, so today we're going to get on to some new stuff. So what have we been doing thus far? So you have just maybe had a week of skiing. I see somebody at least was out on the West Coast tearing it up at Marble Mountain, so that sounds very nice. So what in the world have we been doing so far in this course? Well, thus far in the course, we've talked about computation. We've talked about expressions, we've talked about variables, and then we have gotten to flow control. So if statements and some loops, the while loop, the for loop, and how we can use the for loop to iterate through things. And that's even included some things like list comprehensions. Oh, someone says PyCharm. Yes, yeah, very good. I know some folks also really like PyCharm. Okay, so that's what we've been doing thus far. But what we're going to do next is look at functions. Now you might say, hang on a minute, haven't we already done functions? Well, we've seen one side of functions. So we have seen how we use functions, how we can call functions, invoke functions, how we can put functions to work, but we haven't actually seen how we can create functions. And that's the next thing that we're going to do, and we're going to do that starting today. And then as we go further in the course, we'll look at some other stuff. We'll look at objects and modules. We'll see more kinds of data types that we can use to store more kinds of things, which is going to be lots of fun. We'll see how computers actually represent numbers and how that number representation in binary format, zeros and ones, builds up to a bunch of other stuff. But today, we're going to talk about functions, and functions with a little bit more structure than we've talked about them before. So we will talk a bit more about their semantics. Then we will talk about the syntax, both how we call functions and also how we define functions. We'll talk about function parameters and function arguments and the difference between them. And that's about as far as we'll get today. And then we'll talk about some more things to do with functions on Wednesday. So take a look at this that I'm showing here. Oops. There. That's what I wanted to do. So what's wrong with this code? Oh, I see in the chat that it is someone's birthday. Okay, well, happy birthday. Not going to mention your name only because this is a public YouTube video that anybody could watch, so don't really want to mention students' names in public that way. But what's wrong with this code? Okay, yep, you could just have a loop. Yep, that's true. So someone says no list. So I guess this is assuming that there is a variable called name, which is a string that already exists, or possibly a list. I guess from this code we can't really tell. That's fine. Let's see. Someone says we should use elif. Well, that depends on what we're trying to accomplish. So if what I'm trying to do here is to count all of the e's in a name, so take a name like mine. If I would try to count all the e's that exist in that name, then in fact I wouldn't want an elif, because I wouldn't want the fact that my name started with an e to preclude looking at the next letter, which might also be an e. No, in this case, this is in some sense technically correct. In some sense, there's technically sort of nothing wrong with this if I'm using this as a way to count all the letter e's in a name under a really, really important assumption. So there's only one way that this is correct. Yeah, so someone said the limit of a length of 4. So this is technically correct if we know how many characters are in the name. Someone also suggested in the chat that maybe we want to look for uppercase and lowercase e's. Yep, that's true. If we were actually looking at somebody's name, we would probably want to look at uppercase and lowercase names. But let's just say that I'm trying to write some code for the purpose of counting lowercase e's, and I really actually do want to be that specific and only find lowercase e's in a name. If that's the case, and if I know exactly how many letters are in this name, well, then technically, I guess this isn't wrong, but there are two really important buts. But we don't always know how long a name is going to be when we write a program. So it's one thing to take in someone's name and then to pass that name to, say, the len function and get a number back that tells us how many characters are there, and then iterate over all the characters in that name. That's one thing. That is something where you can make different decisions when you run the script based on how long someone's name is. So you could decide to count up to 4 characters, or you could decide to inspect 8 characters, or decide to inspect 32 characters, depending on how long someone's name is. It's a whole other thing when we have to make that decision not dynamically at runtime, but statically when we write the program. It's not going to be very useful if I have a program that counts e's in somebody's name, but it only works for people who happen to have names that are 8 letters long or something. It could work a little bit better. It could work in some circumstances, like when we're talking about Wordle, for example, where we know the word always has 5 letters, but sometimes we like to generalize and have a program that can deal with more than one size of problem. Also, the other issue here is, so that might have been your initial reaction. Aside from the fact that we may not know how many names or how many characters are in the name, like this code just, it feels wrong to look at, right? The immediate response that I got from people in the chat was, why are we not using a for loop here? Why are we not looping over this? So what's wrong with this program, even if it technically gives us the right answer? Therefore, like if you wrote this on a midterm exam, I would not be able to mark it incorrect because it isn't incorrect, but you did a whole lot more writing than you needed to do. So, why is this icky? And we'll use that as a technical term, very icky. Well, I've said in the notes here that in addition to being inflexible, this program offends our programmer's sense of aesthetics. And aesthetics can actually be kind of important. So things that are unified and make sense together, they also tend to have a kind of beauty that goes with them. And so the aesthetic is not nothing. Now, obviously, I'm not a big maven of fashion or something like that, but aesthetics can matter and style can matter when we're talking about programming, because you can look at this code and say, there's something that's not right about that. So we've got in the chat that it's too long, it's inefficient. So it's actually not inefficient for the computer. The computer is going to do the same amount of work whether I have 8 if statements or whether I have 1 for loop. And in fact, one thing that compilers will try to do in order to make code go faster is to take a for loop and turn it into a bunch of sequential statements. It's called loop unrolling. So it's not that this makes it inefficient for the computer, but it does make things inefficient for the programmer. So our sense of aesthetic is offended because programmers are lazy in a good way. We don't like to repeat ourselves. When we repeat ourselves, we waste programmer time. And remember, humans are going to spend more time looking at your code than computers are, so that matters. So we don't like to repeat ourselves because it's kind of a waste of our time, and a programmer's time is a valuable thing, but also because it gives us more opportunities to make mistakes. If I tape the same thing 8 times, there's a much better chance that I'm going to make a mistake in at least one of those times than if I only have to type it once. So to save time, and also for the sake of reducing the chance of error, there are lots of good reasons that we want to follow the rule of don't repeat yourself. So how about this? What's wrong here? So let's say that I'm trying to do a lexical comparison of words. Now, this is kind of like an exercise that I had given you in the past where I said, now can you write a Python script that will input 2 words and then compare them lexigraphically? So compare alphabetically by the first character, then by the second character, then by the third character, etc. Here we're assuming that the words are the same length. And some of this is just kind of fundamental complexity of the problem. We do need to look at every character in each word and check, okay, is the one in A less than the one in B, or is the one in B less than the one in A? If not, they must be the same, so we'll move on to the next. So there's a certain amount of complexity here that we can't get away from because that's just the nature of the problem that we've been asked to solve. But if I'm using this technique, and students have come to my office to ask questions in office hours about code that looks very much like this first chunk where we're comparing the word A with the word B, and that's great. But if we're comparing A to B and B to C, well, again, this is kind of getting repetitive, isn't it? And what if we had a game where we had to do lots and lots of word comparisons and compare lots of different kinds of words? Well, would we really want to write out this same algorithm 14 times if there are 14 different places in the game where we might need to compare words? Well, no, we wouldn't want to do that. That'd be a whole lot of repeating ourselves. And so just as we've seen that a loop can provide us with a way of creating an abstraction, instead of saying, do this, 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 you can say, okay, I want you to do this thing 10 times or 20 times or 1,000,000 times or however many times it needs to be done. I'm going to define what happens once, and we're going to run the loop as many times as we need to run it. Well, similarly, functions give us a way of creating abstractions. So a function is a procedure that we can define once and then we can use many times. And functions help us stay dry. What do I mean by dry? Does anybody know what dry means, even based on the slides thus far? It means don't repeat yourself. So I've said, ironically, I have repeated myself several times and said, don't repeat yourself. Well, that is what dry means in this case. So if you ever hear programmers talking about the dry principle, or you see it written DRY in all caps, they're probably talking about this. Don't repeat yourself. Okay, so we have seen function calls already. We've been using stuff like this. I'm going to call a function called print, or in the example we just looked at a moment ago, I'm going to call a function called sum. And if I want to pass into the sum function a list of values 1, 2, and 3, well, then those are going to add up to 6. So what happens when we call a function? So we have seen that functions in programming, unlike functions in mathematics, we should look at functions as kind of a box. It's a machine, and there are inputs that go into that machine, and possibly multiple inputs. And then there can be an output that comes out of that machine. So if, and over here I'm going to draw a little hand crank. I'm going to draw it very badly. My apologies. There we go. So if this were the sum function, then I would put in an input here. And so what is this input that I'm putting in from the code that I showed just a moment ago? What was that input that I put into our sum function just a moment ago? Well, it was a list. It was a single value, which was a list. And the list contained the numbers 1, 2, and 3. Oh, someone had... Yes, so some people had in the chat the previous value that we put into sum. So either of those is fine. So we're putting a value into our sum function. And then we turn that crank. We turn that little handle, and we turn the crank, turn the crank, turn the crank. The sum function does its work. It thinks about things. And what the sum function is actually doing is getting the computer to execute a bunch of instructions. The sum function is a set of instructions for the computer. When somebody passes in this value as an input, then do the following operations and then give this result as an output. And the output that we got was the number 6. So a function call is an expression, and that expression evaluates to something. So when we want to read from an analog port, we can call the analog read function. And sorry if it seems like I'm kind of belaboring this point, but we want to make sure that we're really clear on a couple of things and we don't mistake them. So if we have a function called analog read, the input in this case is a number. It's the number of the pin that we're trying to read from, and then analog read gives us an answer. So we turn that crank, 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 crank. It thinks about things. It executes some instructions. A program that's running on the computer talks to a program that's running on your Arduino board over a serial link. They communicate. The program on the Arduino does some work. It executes some instructions, does some stuff, sends a number back, and then eventually that number comes out of our analog read function. And so let's say the analog read function gives the number 150. So if that's a brightness value, it's not super bright. Okay, so the function call, so everything here, the name of the function, open parenthesis, this argument 2, which is the input to the function, the close parenthesis, this whole call evaluates to something. And what does it evaluate to? Well, it evaluates to whatever the output from the function is. And we've also seen that a call can take multiple arguments. So the print function, for example, we pass multiple arguments to that all the time. How do we separate those arguments? What do we put in between those arguments if I want to print multiple things? So if I want to print pint, no, too early in the day for that. If I want to print 1, 2, and 3, I put commas between those arguments. So a function call can take multiple arguments. Now, oops, I don't want to go ahead just yet. So that's how we use functions, and we've seen that already, but now we're going to look at how we create our own functions, how we define these new abstractions, how we define a procedure in a function that we can describe once and say, hey computer, the next time I need to lexicographically compare two strings, here's how we do it. And now I can just call a function from now on if I need to compare two strings. So instead of having to write the same thing over and over, I can write it once and then use it over and over. So this is what the syntax of a function definition looks like. So semantically, we've talked about how a function works, but what's been inside this box has kind of been a bit of a mystery, right? It's a box full of mystery. So how is this analog read implemented? What's inside of it? We don't really know. Well, now we're going to see. And what we're going to see is it looks a little bit like this. So in order to create a function, first we're going to have a new keyword. What's a keyword? Remind me what a keyword is. People are typing in the chat, which is good. Boy, I am grateful for all the technology that we have that allows us to do these remote lectures and the interactive response with Top Hat and stuff, but I do miss some of the real live interactivity that comes from actually being in the same place. Right, so a keyword is reserved by the Python interpreter itself. Good. Okay, so we have the def keyword, and then we are going to have a function name, and that should be a valid name. Now, what do I mean by a valid name? What are the rules that we have seen for identifiers? So the rules of what makes a valid function name are exactly the same as what makes a valid variable name, or in fact a valid module name, or a valid class name, or all kinds of other things. So what are the rules pertaining to a valid identifier? Right, so it can't begin with a number, and we can only use letters, numbers, and underscores. Plus, there's an expanded definition of what constitutes a letter with Unicode. So in Python 2, we could only use A through Z, capital A through Z, lowercase a through Z. Numbers and underscores can't start with a number. But in Python 3 with Unicode, because there are lots of languages that one might choose to write Python in, there is now a very long list of what characters constitute letters for the purposes of an identifier. And those letters are drawn from many, many languages, so it's no longer just the Latin alphabet. No spaces, that's right. Someone asked, can't begin with a number. Oh, right, sorry, we already addressed that. Yes, that's right. Okay, so we have the def keyword, then we have a valid function name, and then we have these new things called parameters. Def, by the way, is just short for define or even define function. And then we have these parameters. And so we've seen arguments to functions before. When you want to pass a value into a function, you use parentheses, and then you have these comma-separated values. Well, we have something that's kind of the other side of that coin now. So we have parameters, which is where arguments go. So we have parentheses, and we have comma-separated names. So these parameters also need to be valid identifiers. Then we have a colon at the end, which is, a trivial thing, but important. Those kinds of trivial details will catch you sometimes. Although Again, this is part of why why you want to have a midterm written on paper, because when I see a missing colon, I say minus a half a point in a big complex question. And when Python sees a missing colon, it says error 0, invalid syntax. Then we often have a thing called a docstring, and we'll talk about what a docstring is in a minute. So def keyword, function name, parameters, a little colon, don't forget, a docstring, and then a function body. And the body is Python statements, which can include or be the keyword pass. Let's talk about each of those things in a bit more detail. Well, we won't talk in much more detail about the def keyword because, well, it's a keyword and it's spelled DEF, and that's pretty much it. And we've already talked about what makes a valid function name. Actually, even before we drill into more detail about what each of these things are, still, I can ask you a top hat question here. Because we've already used function calls, tell me, tap on a function call here. So there's more than one place where we have functions getting called. Now, don't worry about the semantics of exactly what's happening inside the function and how they work. That's the detail we're getting into in just a minute. But even right now, with what we've said so far, we ought to be able to answer this question. Tap on a function call. And there's more than one right answer, and you only have to tap on one of the right answers. All right, lots of answers coming in. I'm going to close this in just a few seconds. Close it out in maybe another 5, 4, 3, 2, 1, and stop. Okay, so we had people tapped on a variety of places, and see this heat map representation, the hotter things are, so the redder things are, the more people who tapped there. And so those are the responses. Oops. Okay. All right. So we had a bunch of taps in a bunch of places, but I will note that the function calls are the places where functions get used. So not looking at the definition, not looking at this use of a function name. This is creating a function. A place where we have a function call would be one of those things that we're already used to doing. So anywhere in this print, so calling the print function and passing the value x into it, that's a function call. Calling the print function and passing in this is y's x, that would be a function call. Calling the foo function, we're seeing that foo was just created up here, but still. So we haven't gone into the details of exactly what foo means, and yet we can see that foo looks like a function name, and parentheses open, there's a value being passed in, parentheses closed. So this, or this, or this, any of those would be valid function calls. So those would be the correct answer. Okay. So now let's go into some more details about how functions are actually defined. So parameters versus arguments. So we've seen arguments to functions before, the values you pass into a function call. Well, a parameter is a variable inside of a function definition. But the thing that's really special about a parameter is that it is initialized by arguments. So here I've defined a little function that is called abs for absolute value. It probably looks a little bit like the the abs function in the math module. The one in the math module is probably a little simpler than this because I've showed a couple of things that we don't need to have here. But this is a function which has one parameter, and that parameter's name is x. So the abs function, when you call it, expects to be passed one argument. So let me, type this. Okay. So now that I have run this script, I've defined a function called abs, and you see it appears in my local variables here. So now I can call the abs function and pass in the number 42, or I could pass in the number negative 42, and oh look, it gives me the same result in both cases. So when I run this function, actually, sorry, I need to, in order to run this under a debugger, there we go. So first of all, we define the function, then we actually use it. So I'm going to step into this function. So what happens? Well, we're going to call the abs function. We're going to take the number 42 and make it negative. So now we have negative 42. We're going to pass that as an argument into the abs function. And where does that abs function show up? It shows up inside of the abs function as a variable called x. And so you see x has the value negative 42, not because of anything inside of the abs function, but instead because negative 42 is the number that we passed in as an argument. This, by the way, this view here that shows us what's going on inside of the abs function and kind of hides whatever's going on in the code that called abs, this is one of the reasons that Thonny is so helpful for teaching purposes, because it lets us focus on one thing at a time. And as we'll see later, when we have functions that call functions that call functions, this feature is going to be super helpful. And I did it again. Sorry. Why don't we try that again? So I typed in the abs function here that was in the slides, and now I'm going to debug what happens when I print abs of negative 42. So we define the function first, then we take the number 42, we make it negative, we take that negative 42 and pass it into the abs function. What do we see? Well, this little window pops up that says, okay, we're inside the abs function, and look, we have a variable, and that variable is called x, because x is a parameter. But we didn't have to say anywhere inside of the abs function that x gets the value 42. We didn't assign negative 42 to x. No, it has whatever value was passed into it as an argument. So here we see in this case, x has the value negative 42. If I wanted to change my function call so that I was passing in the number 10 to abs, then again, I'll define the function, then step into the function, and now you see we have exactly the same function. The function hasn't changed in any way, but the variable x, which always exists inside this function, now holds a different value, and the value it holds is 10. So a parameter is a local variable in a function, and it is initialized by, it gets its first value from an argument. So this value here, this variable called positive, that looks a little bit more like kind of traditional variables that we're used to. So you store a value inside of the positive variable by, well, using an assignment statement. The name of the variable equals or is assigned by a value. Well, x is also a variable. The only difference is that we don't have to assign anything to it. Now we can if we want to. We can change the value in x. So if we passed in x, then maybe we want to increment x or something. We can do that if we want to. So I could instead say that if x is greater than 0, well, we keep it as it is, or otherwise we negate it. Alternatively, I could say if x is equal to 0, then I'm just going to set x to be negative x. That's something that we could do. But a parameter is a variable, but we don't have to give it its initial value. Its initial value comes from an argument. Okay. And arguments are values that we pass into functions. So arguments can be any kind of value. They don't necessarily have to have anything to do with variables. They can be arguments that came from a literal or from an expression, or they can be values that came from another variable or something. We can pass any value as an argument. Okay. After the parameters and excuse me, 2319. Sorry. I'm not sick. I'm a little dehydrated this morning. Too much coffee, not enough sleep. So we have after the parameters and the colon, we have in functions often, it's not mandatory, but we'll often find a thing called a docstring. So very often, the first thing you will find in a Python function is a string literal. And that string literal tells you something about the function. It behaves much like a comment. This is not for the computer. This is for other people. If you have a docstring that's very short, like for example, if I go back into Thonny, and also remember to change my view so that you can see it. I might have a docstring here that is calculate the absolute value of a number. And so maybe that docstring is so short that I don't feel the need to put it on multiple lines or anything. There you go. So that's fine. However, very often we want to go into a little bit more detail because we're going to write functions that have a bit more substance to them, that do something a bit more meaningful than just calculate the absolute value of a number. So very often our docstrings go on multiple lines, and therefore, in order to be allowed to put them on multiple lines, very often we will use a triple quoted string. So remember when we saw string literals, at first we said single quoted or double quoted. Those are kind of the norm. Well, using like an apostrophe or a quotation mark. Well, in this case, we're going to use a triple quoted string for a lot of docstrings. You don't have to, but if you want to have a docstring that's on multiple lines, well, then you do have to. So the docstring is optional, but very much encouraged, because when other people use our functions, then we want them to know what our functions do and how to use them. And in fact, if I were to run this again to define this thing, if I type help abs, well, look at that. Calculate the absolute value of a number. So the Python help function uses the docstring to get information about something. And so if you want other people to be able to use the help function with your functions, then it's a really good idea to use a docstring. Okay, so we have def, we have an identifier, we have parameters and a colon, we have an optional docstring, and then we have a function body. So every function has to have one or more statements. Now, we can, if we have a function that doesn't do anything, or if we have a function that we haven't figured out how we want it to work yet, it can be a useful thing to jot down some of our ideas about a function and use a special statement called pass. So pass means don't do anything. It's sort of like if you're playing a game and you say it's your turn and you say pass. So I might have a function called compare words, and I might write a docstring that says compare A and B lexigraphically, and then more details here. And for now, I'm just going to say pass. This allows me to start thinking about, okay, let's assume that I had a compare words function that worked and did the right thing. I'm going to figure out how to do that later. But right now, I want to focus on how does my game work if I have that function. And so I can put down enough information about the function that I can see how I would use it. I can even write code that calls it, but I haven't actually figured out how to implement it yet. So I can use this pass keyword, which is a statement all by itself. The other new kind of, so every function body has to have at least one statement, but if you want, that statement can be pass, which sort of means, well, don't do anything. The other new kind of statement that we're going to see that we haven't used before functions is the return statement. So we've seen that in at least a lot of usages of functions, we have inputs that go into functions and outputs that come out of functions. Well, how do we produce output from a function? Well, the way we do that is with this return keyword. So if we have an output that we want our function to provide when somebody calls it, we use the return keyword. So our parameters, our input, so somebody, when they call the function, they take arguments, they pass them to our parameters, and then when we're done, we return a value back to whoever called us. And so the function call, function name, arguments, that function call evaluates to whatever value we returned right here. And you notice that can be any expression at all. So it can be a literal, it can be a more complex expression, it can be a variable within the function, it can be any value we like. It can even be a special value called none, which means, well, what it sort of says, it means nothing. So there is a value called none, which is again another keyword. What does our compare words function here return? So we have a function here called compare words. It takes two parameters. So if I want to call our compare words function, I could pass in words like hello and how's it going? And I could compare these two words, but right now there is no return statement in our compare words. Oh, cannot see Thani. Yes, one of these days. So when we have our compare words function, but the compare words function doesn't return anything. So if I call our compare words function and I pass in two arguments like hello and how's it going, then what's that function going to return? Well, it doesn't return anything. It sort of returns nothing. So when we press enter, you see nothing gets printed out. If we wanted to take whatever the result of compare words was and store it in a variable, we can. But what do you think the value of that variable is going to be? The value held in that variable. Give you a chance to type before I open my variables window. Right, and the answer is none. So if you have a function that doesn't return anything, it's as if you typed return none. That has exactly the same effect. So if my result is comparing these two words, hello and how's it going, again, you'll see it returned none. So the return statement means my function is now finished, leave the function, and also pass this value back to whoever called me. So in our abs function here, instead of changing the value stored in this x variable, we could actually do this. So if x is less than 0, then I return negative x. Otherwise, I return the value of x. So what happens when we actually invoke this? So let's debug this script. So first we will define the abs function, and now you'll see abs comes up under variables. We will define the compare words functions. Now compare words comes up. Now let's step into that abs function. So I'm going to take the value -42, pass it into abs, and now up pops this window showing us the execution of the abs function. So first of all, well, believe it or not, that is a statement. It is an expression statement because, well, that statement is just an expression. It's a string literal. So the doc string, if you have a string as the first statement in your function, it is by convention considered the doc string. And so the help function will look at it and stuff. But now you'll see if x is less than 0, So what is the value of x? Well, let's look at our local variables. We've got the value of x is negative 42. So if negative 42 is less than 0, that is true, then we are going to return negative x. So that means we're going to stop running our function. We're going to give back negative whatever x is, so negative 42. So we're going to return the value 42. And look, this statement will never be executed. So it's kind of like how a break statement will cause you to exit a loop. Well, a return statement causes you to exit a function. No matter what else you were doing, even if we were like nested inside of a while this, if that, for something, if we're like in this deeply nested loop within a loop within a loop within an if statement within a loop or something, return means function's done, we're out of here, here's the value that we finish with. So we take that negative x, well, x is negative 42, negative 42 is 42, therefore we just return the value 42. And so calling abs of negative 42, that call evaluates to whatever value was returned, which in this case is the number 42. Okay, any questions about this new function stuff? This is kind of fun. Functions are fun because they allow us to really simplify some things. Even working on assignment 2 right now, you don't have to use functions. You definitely don't have to define any functions. But if you wanted to, you could, and you might find that there are common bits of functionality around things like figuring out what the result or what the feedback to the user should be when this was the word they guessed and this was the word that, or this is the real word and this is the word they guessed. Providing them with the feedback with the yellow squares and the green squares and whatever. I mean, that's something you have to do in a couple of different places at least in your program. So instead of writing the same algorithm down multiple times, maybe it would be helpful to write that as a function. So, that's something that might make things easier for you. Or it might not. That's fine. You definitely don't have to. There's a question here. We can have multiple input arguments, but can we return multiple output arguments? Sort of yes, sort of no. When we get to more interesting data structures like tuples, then we will revisit that question. So that's a very good question, but we will come back to it a little bit later in the semester. Okay, well, I don't see any more questions coming in, so I guess we'll call it a day there. So do check that midterm and do have a look at how you did. And if there are any places where mistakes were made in the grading, there will be regrade requests opened in, I think, tomorrow or the next day, something like that. I've scheduled it. Give everybody a cooling off period to read through it first, check your results. See, the first question you should always ask is there anything I can learn from this that will help me do better on future pieces of evaluation? But if you do genuinely find a place where we made a mistake in grading, I mean, there's, definitely over 1,000 questions that got graded. So could there be a mistake in there? Sure, there absolutely could be. If you do find a mistake, the regrade request mechanism will be available. I think I set it up for this Wednesday until next Wednesday. So you'll have a week to submit those requests. And yeah, so I guess that will be it for today, and happy birthday to those for whom that is applicable. So being at least one student in this class as well as my sister-in-law, happy birthday.